Inverse functions, part 1. In previous sections, we have seen that a function generates a set of y values called a range from a set of x values called a domain. And it's important to note that the domain comes first. So if you mix up domain and range, think about it that D comes before or in the alphabet and X comes before Y in the alphabet. So X values are the domain, Y values are the range. So in this function here, the X values, the inputs, are the domain on the left-hand side, and the Y values, the outputs, are the range on the right-hand side. So D comes before or in the alphabet. In this section, we will deal with the reverse of this procedure by finding the elements of the domain when given the elements of the range. In the mapping diagram, the couples of f are f equals 1, 4, 3, 7, 5, 10, 7, 13. So I've highlighted in yellow 1, 3, 5, and 7. And we can see in our mapping diagram, 1, 3, 5, and 7 are the first set of elements. And then I've highlighted in blue 4, 7, 10, and 13. And we can see the right-hand side the right-hand side set of elements is 4, 7, 10, and 13. So they're highlighted in blue. If we reverse these couples, we get a new function called f inverse. So it's f to the power of -1. F inverse is said to be the inverse function of f. From the mapping diagram, f inverse is equal to 4, 1, 7, 3, 10, 5, 13, 7. We can see now all the y values or the outputs come first. So they are now the x values or the inputs. And likewise, so they're the blue elements. And the yellow elements are now coming second. So they were originally coming first in our function. So 1, 3, 5, and 7 highlighted in yellow. They are now the second element in each of our ordered pairs. So they've swapped positions. The x values have gone into the y positions and the y values have gone into the x positions. For every couple A, B that f creates, f inverse will create the couple B, A. Thus, f and f inverse create points that are reflections of one another in the line y is equal to x. So this red line here is the line y is equal to x. So every point on that line, if we're interested in the coordinates of that line, they are 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and so on. So each x value is equal to each y value. So it's the same number. And you could continue this line, y is equal to x, through the origin, and you would have the point -1, -1, -2, -2, -3, -3, and so on. So this red line, which is called y is equal to x, this becomes a reflection line of our function. So our original function, for example, is this line here, f of x. And the inverse of that we can see is reflected through the line y is equal to x. So we have f to the power of -1 of x. So that's the inverse function of x. And we can see that every x, y point on f of x has now become y, x. Or another way of looking at it is every a, b point or coordinate on f of x has now become b, a. So note, as can be seen from the diagram, the function f has an inverse if and only if it is bijective. So it has to be a bijective function, i.e. the function must be 1 to 1. So one input to one output. So if you're thinking of it in terms of a mapping diagram, every element on the left would have one arrow leaving it and going to only one element on the right. So there should be no element on the right-hand side that has two arrows going to it. So take the function f of x equals x squared. So our typical U-shaped graph. 2, 4 and minus 2 comma 4 are couples of f, the function. So f of x equals x squared. 2 points on that graph are 2 comma 4 and minus 2 comma 4. So the couples 4 comma 2 and 4 comma minus 2 are couples of f to the power of minus 1, which stands for the inverse function. This shows that the inverse function is not a function, as the input 4 does not have a unique output. So 4 is mapping to 2, but then 4 is mapping to minus 2 as well, and that should not happen in the case of a function. Since f of x is equal to x squared is not bijective, it does not have an inverse. How to find the inverse of a function? Let f of x equal 3x minus 2. So let's say this is our function, f of x, and we want to find the inverse of that function. So we replace f of x with y. So now we have y is equal to 3x minus 2. So now we're trying to solve for x, get x on its own. So we're going to make x the subject of the formula. So we're going to follow our normal rules of solving. The only difference is that we have a y contained in our equation as well as an x. But we're solving for x. We want to get x on its own. So we end up with 3x equals y plus 2. And then dividing both sides by 3, we get x is equal to y plus 2 over 3. So what we've done here is expressed x in terms of y, or you could say we've solved for x. We've made x the subject of the formula. So the inverse function of x is going to be equal to x plus 2 over 3. So what we did here was we replaced y with x. So that y just becomes x. So the inverse function of x is equal to x plus 2 over 3 is the inverse function of f of x. So this is our final answer. We can verify that the inverse function is correct by showing that f of 3 is equal to 7. So if you sub 3 into the original function, you get 3 multiplied by 3, which is 9, minus 2 is equal to 7. And f inverse of 7 is equal to 3. So if we substitute 7 into the inverse, so we end up with 7 plus 2, which is 9, over 3. 9 divided by 3 is 3. So it works out. Example 1. Part 1. If f of x is equal to 5x minus 3, find the inverse function of x. Part 2. Hence, show that f inverse after f of x is equal to x. So here we see composite functions coming into inverse functions. So part 1, let y equal 5x minus 3. So all we've done here is swapped f of x for y and then just wrote down the 5x minus 3. And now we're going to solve for x. So I'm going to bring any x terms to the left and any non-x terms to the right. So it's similar to the rule, letters to the left, numbers to the right. But this time the y is obviously a letter. That's going to go to the right-hand side because that's the non-x term. So 5x comes to the left and becomes minus 5x. Minus 3 is already over there, so that just stays as it is. And y comes over to the right and becomes minus y. So we move the x term to the left and we move the rest to the right. Next, we're going to divide both sides by minus 5 to get the x on its own. And obviously I want a positive x over here. When we want to solve for x, we want a positive x. So it works out that dividing by minus 5 will make that into a positive x. So we end up with x equals minus 3 minus y all over minus 5. And then I'm just going to tidy up the right-hand side with the minuses. So a minus divided by a minus gives a plus. So we can just rewrite this as positive 3 over positive y over 5. So if you're able to tidy up any minuses, you should. So solving for x, we get x is equal to 3 plus y all over 5. So x gets replaced with f inverse of x. And then the y gets replaced with x. So the inverse function of x is equal to 3 plus x all over 5. Part 2 wants us to show that f inverse after f of x is equal to x. So we know from the question that f of x is 5x minus 3 is equal to 5x minus 3. So we're going to substitute that into the inverse. So we're going to work out f inverse of 5x minus 3. And we know from part 1 that the inverse function of x is x plus 3 over 5. So we're going to substitute that into 5x minus 3. So replacing that x for a set of brackets, make sure you use brackets. We have 5 multiplied by x plus 3 over 5 minus 3. And then multiplying out, 5 times x is 5x, 5 times 3 is 15, all over 5 minus 3. And then simplifying, dividing each of these terms by 5, we get x plus 3 minus 3. The 3's will cancel, 3 minus 3 will cancel, and we're left with x as required. For example 2, we're going to use this yellow box here in the corner to help us. So for any two functions, f and f inverse, then f after f inverse of x will equal x, and the inverse, so f to the power minus 1 is the inverse, so f inverse after f of x is also equal to x. So this is something that you should learn off. Sometimes it's given to you in a question to show that this is the case, but you should learn this off by heart. So if you substitute f into the inverse, or you substitute the inverse into f, you should always come out with x. So you should learn this off. The diagram on the right shows the reflection of the curve f of x equals x cubed plus 1 in the line y is equal to x. So we can see our dotted black line is the line y is equal to x. So every point on that line, every point will be the same value. So for example, we'll have 0, 0, 1, 1, 2, 2, 3, 3, and so on. And then negative values, minus 1, minus 1, minus 2, minus 2, minus 3, minus 3, and so on. So this becomes a reflection line. So we want to find the equation of the inverse function of x. So instead of f of x, we're going to have y. So we just replace f of x with y. So we have y is equal to x cubed plus 1. And now we're going to solve for x. So we're going to bring the x terms to the left and the y terms and the constants to the right. So we get minus x cubed is equal to minus y plus 1. And then multiplying across by minus 1 to get rid of the negative x, we want our x cubed to be positive. So we get x cubed is equal to y minus 1. And then bringing over the cubed, it becomes cube root. So we get x is equal to the cube root of y minus 1. And now we're going to replace y with x. So the x becomes f inverse of x. And then the y underneath the root becomes x. So the inverse function of x is equal to the cube root of x minus y. So highlighted here in yellow is our inverse function. And we can see that it's a reflection of the original function, which is in red. So the original function we started off with was y is equal to x cubed plus 1. So it's our y is equal to x cubed graph, just moved up one step. So y is equal to x cubed would go through the origin 0, 0. So it's just been moved up one step vertically. So we can see that our inverse is the reflection of the original curve in this mirror line, the mirror line being y is equal to x.